Good evening, everybody, and welcome to the Astro Imaging channel. My name is Molly Wakeling, and the TAIC team that we have here tonight with us includes Eric Coles, Timothy Hutchison, Patrick Spencer, Alex McConaughey, and we have a couple absences tonight as well among the team. And our guest speaker tonight is Greg Crinklaw, who he's going to talk about how to best optimize your image capture, including things like camera settings and planning your targets, using lessons that he's learned from writing the SkyTools software package. He lives in Cloudcroft, New Mexico, and is a developer of SkyTools. This is on top of having a couple degrees in astronomy and physics and working at NASA as a software engineer on the Mars Orbiter camera, which is very cool. Before we go over to Greg, I won't pull up the schedule because you guys can go to our website, theastroimagingchannel.org, and see our calendar, but I'll quickly go over what we've got coming up. So next week, we have Craig Stocks joining us again to talk about image processing in both Photoshop and PixInsight. So we won't settle the debate once and for all, but he'll show us the good things about both. After that, we're going to have Adam Block back with us, which is always exciting, to talk about the new color mapping script for PixInsight. And then we're off Thanksgiving weekend and then into December. Yeah, don't forget to, over the course of this live stream, to put in your questions. The good part of having the live stream is you get to ask questions of our speakers. So if you have any burning questions or other kinds of questions, you can put them into the chat and we will field them to Greg for you. Make sure they get asked and answered. And yeah, don't forget to hit the like button so that more people will get recommendations to watch the Astro Imaging channel videos, and we'll also learn all the cool things that you are also learning. So without further ado, Greg, take it away.
Hello, everybody. I'm Greg. I guess I should share my presentation now. Always the most delicate part. Hold on. Of course, I got an error.
Looks good here.
Okay. All right. We're good. All right. Well, I'm really happy to be here. And I would like to thank you guys, the organizers, and Alex in particular, for inviting me. You already said a little bit about my background, but I want to reiterate it just a little because some of the things I'm going to say are going to sound a little different. Back when I was a professional astronomer, in my very short career as a professional astronomer, I ended up publishing papers using every kind of equipment I could get my hands on, and that was actually quite a while ago. So I did photoelectric photometry. I did photographic photometry using photographic plates, and of course CCD photometry and CCD spectroscopy. And of course I also developed image processing in support of a NASA mission. So I hope, unless I've gotten something wrong somewhere, I hope I know what I'm doing. Last time I spoke on this channel, I introduced my new SkyTools 4 imaging software. And it may say version 4, but that was actually the first version of SkyTools Imaging because I split it from the visual. And I've been working ever since then on identifying its weak spots in order to improve it. And I started working directly on SkyTools Imaging 4.1, which is basically the 2.0 version last February. There are lots of improvements, but the main features that people are going to see is direct support for NINA, the NINA Astrophotography suite, and new tools that will make planning your imaging more efficient and straightforward. So the last 10 months have been a journey. I have gone down some massive rabbit holes, changed a lot of code, and I've learned a lot in the process. So the idea is to share what I've learned about taking better images. So we're going to start here. This just occurred to me yesterday because I was actually thinking about writing such a tool myself, and I'm kind of surprised nobody else has done it yet. I guarantee this is coming. We already have AI noise removal and star removal. What will change things for a lot of people is AI tools to stretch images to display maximum detail. And I think that's just coming around the corner. Once we have that, it's going to be a lot easier to process images. And I have a tendency to take too many more images than I can process anyhow. So I'm kind of personally looking forward to that, kind of taking all the work out of it. Hopefully it takes the work out of it, but not the art. I mean, there is a difference between things that are just difficult and time consuming and actually coming up with a really nice final image. So what my software does that makes it completely different from every other software product is that it uses a scientific model of your imaging system. So you start with the spectral properties of the target. You take that that light, you run it through the atmosphere, which puts a fingerprint on it. You then go through the telescope optics. You go through the filter. Then you end up at the camera and the detector. And at that point, you can predict the signal. And you can, of course, predict the noise, which means you can predict the signal-to-noise ratio. That's the idea behind SkyTools Imaging. And so when you ask a question like, what's the best exposure time to use? The problem is people have generally focused on one aspect of the system in order to obtain an answer, because usually that's the only thing you can do. So there's all this advice out there about the best sub-exposure time to use, but it comes from a narrow point of view. And so the advantage of being able to consider all the different possibilities, the signal, the read noise, light pollution, saturation, clipping, all that together, can provide a more complete perspective. And that's one that doesn't ignore one factor over another. So that's the kind of things I'm going to share tonight, things that come out of this model. Of the noise, the main things that are main sources of noise in your images are the readout noise, which scales with the number of images you take, because each image adds noise. And then the sky noise, which scales with the exposure time. And we're going to get back to that later. That's going to be important. If you can produce a signal-to-noise ratio, we should talk about that real quickly. That's a number that tells you the accuracy of your measurement or the quality of your image. And a higher number is always better. The parts of the image with a higher signal-to-noise ratio have a higher, the parts of the image, this is something you don't normally hear. The parts of the image with higher signal have a higher signal-to-noise ratio. In fact, to be meaningful, to really talk about the signal-to-noise ratio, you can't talk about the signal-to-noise ratio of your image as a whole. You have to talk about the signal-to-noise ratio of each part of the image. This scale over here, generally, I find that a signal-to-noise ratio of 20 provides something that with some noise reduction you can usually get by with. Signal-to-noise of 30 looks pretty good, and a signal-to-noise ratio of 60 is very nice. And here's sort of a blow-up of those three. So I usually try to aim for 20 unless I can do better, and then I do better. So what's the first thing you can do when you've got something that can predict the signal-to-noise ratio of your image based on where you're at, what night you're imaging, your telescope, all that stuff? Well, the first thing you can do is determine what kind of things you want to image. And where that comes in is that each imaging system is better at some targets than others, especially when we're talking about extended objects. So an object like a nebula, the problem is there's a trade-off between the image scale and the exposure time. So imagine what's happening is if it's only covering 3 pixels or 4 pixels, it's very tiny on your image, all that light is going into those 4 pixels. If you spread it up so it's covering 4,000 pixels, now each pixel is getting a little tiny piece of the light. So you've got to find, you want something with a good image scale so you can see all that detail, but not spread out so much, depending on your imaging system, so that you can't get a reasonable signal-to-noise ratio in any of those pixels. So we can use this model to find those objects near the sweet spot. And that's the first thing that it does that's useful. The next thing it does is help you determine when to image. So when to image depends on the altitude of the target, the dark period of the night, the properties of the telescope, etc., and also the spectral characteristics of the target object. This isn't generic. This is each object is different. So what most people do is they just say, well, I'm going to go down until I reach a certain altitude and then I'm going to stop. But not every filter and every object needs to stop at the same altitude. So how low should you go before you stop? We're usually just guessing. This will give you a really good idea. Also, if you're going into twilight, similar question, how far into twilight can I go before I stop? And that's going to be different in an H alpha filter than it's going to be in a luminance filter. So here's a sort of a graphic that is often found in my software for a given night. So midnight's in the middle here. This is the altitude of the sun. This is the altitude of the moon. And this shaded background here is shaded according to the model I use for the sky brightness. Excuse me. This red dashed line is the altitude of our target object. The most interesting line on here is this blue line. This is what we call the imaging quality. And what we do is we calculate for a completely dark night, high in the sky as it gets, way up here, good weather, how much of a signal to noise ratio can we get, say, in a 5-minute exposure? And then we go and we calculate what the signal to noise ratio is every 5 minutes during the night. And then we plot the ratio of the two. So if it's way up near the top, where the ratio is almost 1, you're at the best time of the night. You're at almost your optimum best imaging. And you can see here what's going on. We've got the moon up, our object is starting to rise, the quality is 0, but it starts to go up pretty quickly, but then it levels off. That's because the moon's up. But it's rising and the moon is setting. So they're on opposite sides, parts of the sky. So as time goes on, the quality improves and improves until finally the moon sets and it reaches its peak for the night. So this part here, between 4:30 and 5:30, is probably the best part of the night to image, and then it drops off. So that's how we can use this model to tell us when the best time of night is to image. And when we do that, we start looking at individual filters and we get different answers. So this is the exact same night, exact same equipment, but for different filters. I'm gonna zoom this in here a little bit. And what we've got here is we've got this blue quality line, but there's this bar down here that summarizes the quality of that we see in the blue line up here. So this green bar here, this bright green area, is the best part of the night to image. This dark green area is still pretty good. So we could image from here to here in this R filter. Or if we wanted to just do the best part of the night, we could image from here to here. In the L filter, it's a different story. It's shorter period for both and a much shorter period where it's at its best. And that's because the moonlight affects it more. In the B filter, well, I didn't know I could do that. The B filter, it's never good enough. There's too many bad things going on. And in the H alpha filter, that actually might be a weather thing. In the H alpha filter, it's got this long period of night where you can image all you want. And so if you're going to make a schedule knowing this, and these are the filters you want to do, you're going to start with this one because it's the first one that reaches the optimum time of the night. Maybe you'll image to here and do this filter. And you can just keep going. Or maybe you'll stop and do this filter. And maybe you'll save this filter for a different night. So it's very dependent, it turns out. The quality is very dependent on the filter you're using and the quality of the target object. Okay. So at this point, we finished the first sort of little thing that I wanted to talk about. Does anybody have any questions?
Greg, when you talk about...
No question yet.
Actually, I have a question. Greg, when you talk about 60, 40, what's the units? Are you talking about decibels? Are you talking about dB there? Or
okay,
what are you measuring?
Which part of what I'm measuring? Oh, the quality? No, that's just a straight ratio. So
straight ratio.
It's just a straight ratio. So
60X.
1 would be at the top. And that just turns out that works pretty well. So the quality is 1 at the top and it goes down to 0 at the bottom.
I'm sorry, let me try and ask my question a little better. Earlier on, you said that a signal to noise ratio of 60 was pretty good,
Right.
40 was okay. Are you talking about dB?
No, I don't use dB. So that's your
Or what are you
standard.
measuring?
That's your standard signal to noise ratio, just defined in the standard way. You take the signal and you divide it by the noise, square root of the variance of the noise.
Square root of the variance of the noise.
Yeah.
Got it. Thanks.
Okay, Craig, I have another question. So if this is a competition for food on the table, all the filters are going to try to get to the same time of night. And so how do you decide, aside from the fact that in HA you can do a lot more over a longer period, what's your decision tree like as far as what goes first?
You can, we're not going to really talk about it tonight, but the SkyTools has a scheduler. And what you can do is you can sort of define it any way you want. So you could fill out that schedule based on that information manually. But what you're getting more to is, let's say if I auto schedule, which is commonly done, what's it going to do? And it looks at all sorts of things. It looks at how is the availability of this filter better tomorrow night and the next night and the next night, or is it getting worse? So if you look at this object here, it's in the coming nights, it's going to, this whole curve is going to move to the right. So we're kind of losing this object. We're going to lose it the best time of night. It's going to be during the day soon. So that gives it some urgency. And it looks at that, and it looks at the different filters. It looks at what the moon's going to be doing. And it says, okay, our top priority is this filter. And of course, it also looks at different objects. Because if you do it this way, it could also be looking, different objects, but different projects. It could be looking at filters from other projects as well. And in fact, one of the ways that makes this really efficient is if you have multiple projects and just let it work away on the ones that it can. Does that answer your question?
So do you set those parameters as to what the priorities are, what it should look at, or
you can set a priority for a particular object? But other than that, the parameters are fairly straightforward. It generally, in something like this, it will start with the first one. So it's going to say, let's say this is the first thing it's starting that night. You can tell it that B is okay. This is called the B period here, and this is the A period, the quality grades. If you tell it B is okay, it might put it here, but sometimes it looks at it and says, no, you really want only quality, because only high quality observations, because you're going to have plenty of other opportunities to get high quality observations. In this situation where it's in the early morning here, it may go ahead and give you the B. So yeah, it does do some thinking itself, and there's no way to override that, except you can go ahead and build the schedule yourself manually. You can just say, I want to start right there in that filter. And
okay.
Go ahead and build it. That it?
Yes.
Moving on. So I've been thinking a lot about stacking lately, and I had some questions. Excuse me. I guess these are things that I probably should have already known the answers to, but they're the kind of things that kind of nibble at the back of your mind, that I'm not 100% sure about. So I came up with this list of questions that I wanted to answer when I started this process. And I had this crazy idea that there was a point of diminishing returns when you stacked images. As you stacked and stacked and stacked and stacked and stacked, you would reach a point where you were kind of done. There wasn't much point of continuing on. So that was my first question, is that something that's real? The second question is, will adding images of a lower signal noise ratio to your stack degrade the overall quality of your stack? Third question was, should you stack image stacks? And what we mean by that is, let's say you took 50 images the first night, you stack those all up, and then the next night it was clear you didn't expect it to be, and now you got 50 more. Should you start over and stack all 100? Or is it okay to stack the first 50 and then the second 50 and then stack those two together? And lastly, how do you calculate the signal to noise ratio for an RGB color composite image or an LRGB? So those were the questions that I had going in. So regarding the point of diminished returns, this is the simplest formula we have for stacking images. It's just the square root of the number of images times the signal to noise ratio, which I'm using SN here, of an individual image. And if you graph this, it's not asymptotic. The short answer is no. You can always stack more images. If you've got 50, go ahead and make it 60. So more images will always improve the result, unless your result is already so good. Let's say you got a signal to noise ratio of 100, that there's no point of continuing on. But that never happens. And here's why. You might have a signal to noise ratio of 100 for that bright center of that galaxy, but you're not going to have a signal to noise ratio of 100 for that very, very faint outer extreme. That's going to be much lower. So you can always continue stacking to try to increase the signal to noise ratio of the fainter parts of the image. So the second question was, will adding images with lower signal to noise ratio to your stack harm the total signal to noise ratio? Now, people are used to taking images out, but that's usually because of poor tracking or maybe there's some sort of defect, physical defect to the image. The seeing was much worse at that point, so people take those things out. But what if the signal to noise ratio is just lower? And we saw that formula earlier. This is the actual formula for stacking 4 images. We take the signal to noise ratio of the first image and square it, signal to noise ratio of the second image and square it, etc. Add all those up and take the square root. So in this case, each signal to noise ratio could be different. If you look at this mathematically, you'll see that the signal to noise ratio could be very small, but it's not going to be negative. And even if it was negative, if you're multiplying it by yourself, well, you're multiplying it by itself, so it's going to be positive. There's no way for this to be so small that it that it harms the total. No matter how small it is, it's going to increase the signal to noise ratio. It'll just be by a little tiny bit. So you can always increase the signal to noise ratio, and that means you can stack images of different exposures, sub-exposure times. So if you got 10 300-second sub-exposure times, you could, in theory, go ahead and stack a whole bunch of 60-second exposure times right in there. And in terms of signal to noise ratio, it's okay. It's not going to matter. So should you stack image stacks? Again, looking at the map, this is how we would stack 4 images together. Let's take 2 at a time. So this would be the signal to noise ratio for the first 2 images. This would be the signal to noise ratio for the second 2 images. And then this would be our final signal to noise ratio, where we just stack the 2 stacks together. And if you do the math, these 2 numbers work out to be exactly the same. Now, in practice, it's not going to be exactly the same, especially for small numbers of images. But for large numbers of images, it's going to be more or less the same answer. So yes, you can go ahead and stack more than one stack of images together, and you're going to get pretty much the same answer as if you stack them all from the start. So what is the signal to noise ratio of a RGB color composite image? And this is the formula. And I'm sorry for showing you so much math. It's just here to point at. Those of you who are mathematically inclined will see some red flags here. We've got inverse of the numbers. So this is the signal to noise ratio of the red, green, and blue. We're taking 1 over that and then squaring it and adding to this reciprocal of the next one and squaring it, and the next one and squaring it. So what happens if one of them is small? Let's say the signal to noise ratio of the blue image is much smaller than the others. We're going to take 1 over that, which is going to make a big number. And then we're going to square that, which is going to make a bigger number, which is going to dominate the other 2. We're going to take the square root of that. And then when we take the final reciprocal, that's going to be a bigger number. When we take the final reciprocal, we're going to get a tiny number. So what this means is if you have a stack of blue images that has a much smaller signal to noise ratio than the green and the red, you're going to get a lot of color noise. It's going to drag the total signal to noise ratio down. So it's a really good idea to try to get the same signal to noise ratio in each of your colors. And that's going to mean you're probably going to need to stack one of them a lot longer. This color noise is also the same thing as the signal to noise ratio for your RGB composite image. But LRGB to the rescue. You can take that number that you get here for the color noise, square that and add it to the signal noise ratio squared of your luminance image, and we're back to where we were when we started. This can't hurt that. It can only make this bigger. Okay? That's why adding that luminance image to your stack works so well. Okay, so that's my thoughts about stacking. Does anybody have any questions?
Actually, we do have a couple of questions. Let me go through them for you. Greg, let me just read what he says. What about just a one-night project with best selection for that night and still covers, say, narrow band filters to at least get an image? You have only one night. What do you do?
Well, I'm not sure. Well, we'll probably get to that in a little bit. But what you do is as much as you can do. But it's going to come down to if you're doing a color composite image, and I don't know what kind of image he was talking about. But if you're doing a color composite image, you're going to have to decide how much of that night you're going to spend on red filter versus blue filter versus green, and whether or not you're going to want to do a luminance. And gee, it would be really great if we had a tool that would tell us the results of, say, I've got 5 hours tonight. What will give me the highest signal to noise ratio image? And that's actually what I've been building. So we'll show you that at the end.
Greg was saying he's a mobile person and he sets up each night in a different location, and he just wants the best schedule for the single object. And Chandrasekhar says, sorry, I still have to comment on the SNR graph. I think 50 means 50% of the max. Is unit 1 correct, or how do you measure the SNR?
Yeah, it's just a ratio, so 50 to 50%. And what I did is I did a lot of testing with real images and determined where the break should be in the quality. And it's really all up near the top. If you're above 90%, you're really, in fact, it just works out where if you're above 90%, you're in the high quality area. And that's really what we should be paying attention to. If you're above 80%, you're in the pretty high quality area. And if you're below that, you shouldn't be imaging. That's pretty much how you interpret those numbers. So you want to be at least at 80% of the straight ratio of between your two signal and noise ratios. So the signal and noise ratio of your best night divided by the signal and noise ratio, I'm sorry, the other way around. Signal and noise ratio right then divided by the signal and noise ratio of your best night.
And I have one more comment. I've looked at this issue on and off for years, and the approach is not mathematical, but simply night after night plotting the SNR on a graph. And when the SNR starts to plateau, you're done. And you can't really improve it much by getting more and more subs to add up.
I don't understand that.
So if you take one night of luminescence, you have the SNR. Take 2 nights, add them together, plot the SNR. You will get a curve that will plateau off after a few days. And you've kind of reached the limit of how much data you should collect. Again, a non-mathematical approach.
That's not my experience with the math. With the math or the real images. You know, probably most of the images I do these days are just test images to show that everything is working properly. Yes, I think maybe I explained it wrong. Yes, it does. You do reach the biggest increase in signal to noise ratio is when you stack your first two images. And then the second biggest is when you stack your first three, and so on. So the impact of stacking one more image becomes less and less and less. But you could look at that in terms of doubling the number of images you're stacking. And yes, it becomes less and less and less, but you can always improve it. That's the point. And it really doesn't taper off to a point where you can't improve it anymore. That's not in the math.
Because it doesn't asymptote, right?
It doesn't.
Yeah.
Well,
It
of
might
course
look like it does if you plotted it the right way.
but we don't have infinite time in the skies. So you have
Exactly.
to decide how much data is enough. Chandrasekhar has another question. What tools do you use to measure SNR?
I've used various things over the years, but right now I'm using PixInsight. I forget what it's called. I haven't done it in a month or so because I've been doing other things, but there's a tool in PixInsight, and I was using that. I also have tools I've written for myself that will go into they're a little more crude, that go into the FITS image and extract a signal to noise ratio in a square area. It's choosing the area to measure the signal to noise ratio, and we're going to see that a little bit. That matters. I'm not. Several people, I think, have referred to. I only have one night, and that's great. That's sort of what the software is all about. Is how do you get the most out of that night? And one person commented that they only want to do one object a night. If that's all you want to do, that's fine. But it's way more efficient to if you're going to do multiple objects over the course of a year, figure out what those projects are and start doing parts of them until you complete them, because otherwise you're going to end up getting lower quality images. The whole point of this is only image during the high quality parts of the night. And yeah, if you don't really want the highest quality images possible, you can go out and image anytime you want. Any other questions?
Not right now. So
okay,
please
I'm going
go
to
ahead.
move on. I should, yeah, whatever. All right, now we're going to talk about sub-exposure time. You think that was controversial? Wait till you see my answer on this. And I have math to prove this up and actual images. People always ask, what is the best sub-exposure time to use? And they get a lot of really complicated answers. And here's mine. Longer sub-exposure times are always better, except when they're not. And this, except when they're not part, comes down to practical considerations. Is the sky so bright that you're going to get saturation and clipping in the bright parts of your target? Are there lots of airplanes and satellites, so you really don't want to go that long? And of course, tracking errors, things like that. Those are the things that determine how long your sub-exposures should be. Not all this other stuff that you've heard about. I know that's controversial, but let's going to move on to that a little bit. Now I'm going to say something else even more controversial. There is no such thing as an optimum sub-exposure time. Doesn't exist. And now we're going to take a moment to look at this beautiful image and take a deep breath. Now, why are we looking at this? Because I took this with my Canon T7i a couple of years ago, 2020, and not only is it a better comet image than I ever thought I would get with my DSLR, but I got this lightning in here too. So because of that, I showed off every chance I can. All right, so let's remember, this is me in the 1980s. I've been doing this a long time. I've learned the basics of obtaining data on detectors from one of the top people in the field way back in the 1980s. My intuition, going back, and this telescope, I hung off the side of this telescope, taking 4-hour exposures with plates. And the CCD revolution had already started. I just was doing that because I could. And we had all the equipment there. When CCDs came along, people called it the CCD revolution. And they told us that, hey, CCDs are way more sensitive. You won't have to do 4-hour exposures anymore. And that's true. But you know what? If you took 4-hour exposures, you'd really get something else. The thing is it's usually impractical to take 4-hour exposures. But my intuition still in the CCD era told me that longer exposures were better. So now we come along to the CMOS cameras, and we have another revolution, and we're promised a similar thing. We're promised that we could take very short exposures and stack those because the read noise was so much lower. And that was going to help us, especially in light polluted locations. Okay. So I'm sure people on this channel have explained in detail the theory of sky limited exposure times and the optimum exposure time for cameras. And I just said that stuff doesn't actually work. So I'm going to show that. I'm going to demonstrate it. This is our test setup. It's iTelescope T72 in Chile. And I think it's rather beautiful. This is an iTelescope. If people aren't familiar with that, it's a company that rents telescope time. Because of their large number of different telescopes, I use them a lot for my testing, so I can try a camera with this imaging system with a color camera one day, or something like this on another, so I can make sure that everything is working right. This is what we're going to use for this test. I chose it because of the weather at the time in the Northern Hemisphere was pretty bad. And I found a great object I wanted to use for testing that was in the Southern Hemisphere. And this is a big, awesome telescope, so why not? This is our test subject. In this subject, we have both O2 and H alpha emission. The O3 is about 2.3 times as strong as the H alpha. It turns out, remember way back at the beginning, I said if you talked about the signal-to-noise ratio, you needed to talk about what part of the image you were talking about, because the signal-to-noise ratio, shockingly, depends on the signal, right? So these bright white areas in here are where the signal is the strongest. So we need to start breaking our images up and say, this is the bright part of the image, these white parts. This part out here is actually the main part of the image. I call it the main extent. That's sort of the second brightest part of the image. And then out in here, that's much fainter. And way out over here, there's some really faint, very faint parts of the image. When we talk about signal noise ratio, we need to look at each of those independently. I call this an exposure table. It's one of the things that I developed for SkyTools 4.1 imaging. And what we've got here is we've got, for that target object, we've got signal noise ratio across the top and the brightness of the various regions over here. And what it tells us is how long you have to expose to reach that signal noise ratio. So for our sort of beginning target level, signal noise ratio of 20, we have to expose for 10 minutes. For the brightest regions, for the main regions, it's going to be more like 40 minutes. This is in just one filter, the L filter. For the faint regions, we're looking at 17 hours. And for the very faint regions, forget it. Not at this image scale with this telescope, even though it's nice and big. We're not going to get a signal noise ratio of 20 anytime. So that's one use for this. Now we can look at it and we can say, well, what am I going to get? Well, for this, I'm going to get mostly the bright regions and the main region and some of the faint, a little of the faint. After that, we're not going to get anything. Now, this table is also for this L filter. We call this the sub-exposure time signal noise ratio deficit, or the percentage loss of signal noise ratio for a given sub-exposure time. And so we start over here on the right, because every sub-exposure time I've ever checked This is the list of all the sub-exposure times that are available for this particular telescope. Goes from 30 seconds to 10 minutes. The longest ones always give you the best signal to noise ratio, if you ignore all the practical concerns. So we start with the 10-minute exposure over here. At 9 minutes, we lose 1% of our signal to noise ratio. At 4 minutes, we lose 10% of our signal to noise ratio. And what I'm talking about is stacking a bunch of 4-minute exposures up to the same number of 10-minute exposures so that we're comparing the same total exposure time. So if we stacked 20 30-second images and we compare that to one 10-minute exposure, we lose 50% of our signal to noise ratio. Under these conditions, for this object, in that filter, in this telescope, and at a very dark site, it's important to take all of those things into account. So this is a pretty useful table as far as determining sub-exposure time. Notice that the best are always the longest. So here's my test subject. This is a combination of two 10-minute exposures, and this is a combination of 20 60-second exposures. And it is going to be really hard to see here, but if you go in and measure it, if you go, here is what I'm looking for. If you look at just this one, you look in here, you can see a lot of noise. And then look in here, you might be able to see there's a lot more noise. And when we measure that, this one over here had, if we take the signal to noise ratio at a spot in here, actually for that, I use the bright spot, so the bright spot right there. Measure the signal to noise ratio, then measure the signal to noise ratio in the stack of 60-second images. What we get is that this image has 39% of the signal to noise ratio of this image at exactly the same spot. And the software predicts 40%. And I'm going to call that a win. I mean, none of this is exact. There's so many things going on here, but it's the overall effect that matters. So this tells us that the predictions made by this table are correct.
Greg, could you go back to that image for a moment, please? I'm not wrong. Those are elongated stars in that right-hand image.
Yeah, yep. And there's your practical considerations. Now that probably hurt the signal to noise ratio, or did it help? I don't know. We'd have to think about that for a minute. I don't think it really made a difference in the signal to noise ratio. But yeah, you probably don't want to be doing 10-minute exposures on this telescope. It actually doesn't use active guiding. So in that case, I would use 5-minute exposures. But yeah, that's true.
Is that a 20 or a 24 plane width?
I think it's a 24, but I'm not 100% sure. There's so many of them and they keep changing.
And they're not using guiding on that?
No.
That's kind of going to mess up all your calculations, isn't it?
Why is that? Oh, they're guided. They're not actively guided. So what's happening is they've got the mount so well tuned that they don't have to have a guide camera to make small adjustments. Even through a 10-minute exposure, most of the time it works. This might be flexure or something like that. I don't remember the situation that night. I might have taken them at different times. Well, no, that wouldn't make sense. Anyhow, that's neither here nor there. As far as the signal to noise ratio, that's what matters in here. We're talking about signal to noise ratio only right now. Okay, so that was a dark site. Let's look at light pollution. So I've got 3 tables here. I'm going to have to zoom in a minute. One is for a very dark site, Bortle 1 to 2, which is where that telescope is, a Bortle 6 and a Bortle 9. We've done all of the exact same calculations. And then now let's look at comparing them. And I'll compare a Signal noise ratio of 20 in the brightest regions. At a dark site, it's going to take 10 minutes. Signal noise ratio of 20 in the brightest regions. The only thing I changed was the sky brightness is now going to take significantly longer, 54 minutes. And here at Bortle 9, which is admittedly very extreme, is going to take 7 hours. So that shows right there that the main effect of light pollution for a broadband filter, that's all we're looking at right now, is to make it so that you have this penalty. You're going to have to expose much, much longer to get the same signal to noise ratio. Now, the other part of this is this exposure deficit idea. So we already looked at a 10-minute exposure at this dark site. If we use a 30-second exposure, we lost, for the same total exposure time, we lost 50% of our signal to noise ratio. Now let's look at the Bortle 6 site. Do the same thing. We only lost 20%. That's interesting. We go down to the Bortle 9 case. We go over. We only lose 3%. So even though there's this huge penalty for having all that light pollution, what it tends to do is make the sub-exposure time you use moot, because the sky is so bright. It's all of the noise is coming from the sky brightness rather than the read noise. I'm going to move on here and look at these graphs. This is the time to reach signal noise ratio of 20 at versus Bortle scale. So for Bortle 2, we get to signal noise ratio in this luminance filter very quickly. Bortle 6, it takes 50 minutes. Bortle 8, it goes up very quickly. So we get the same thing in the H alpha filter. It just takes a little longer. It's not as dramatic. And that's for the brightest parts. For the faint regions, we get similar curves, right? But just the numbers over here are different. You're going to have to expose a lot longer. And how are we doing on time here? Okay. So moving on, the effect of read noise. How does that affect our results? And I think everybody can read that. This one, we just took the same exact imaging system. This one just has a read noise of 3 electrons, and this one has per second, and this one has, or 3 electrons, and this one is 13.5. So let's go to our brightest regions, 10 minutes, and down here, it's going to be 9 minutes. So that improvement of the signal of the read noise didn't get us a big change in the bright areas. But let's look at the faint areas, very faint regions. Well, okay, let's look at the faint region, 17 hours to get a signal noise ratio of 20 versus 11 hours to get a signal noise ratio of 20. So that low read noise helps, but it helps more with the fainter regions than the brighter regions. Why is that important? Because if you've been paying attention from the high, well, okay, we're going to get to that in a minute. I got ahead of myself. Never mind. Now let's look at the exposure time deficit. Remember, this is for a dark site. We're comparing 2 different signal noise, 2 different read noise values for the exact same camera, and everything else is the same. So 10-minute exposure versus 30 seconds. We're familiar with this one, 50%, and 10-minute exposures versus 30-second. The difference is only 8%. So the lower read noise, this you would kind of expect this, means that we can use the shorter exposure times. That is correct for the dark site. Now look what happened when we go to the light polluted site. Now, for the bright regions, it's going to take 7 hours to get to the signal noise ratio of 20. And that's with the 13.5 read noise. For the 3 read noise, it's still going to take 7 hours. It doesn't really make any difference. Now, this is Bortle 9. We're going right from one extreme to the other. but it sort of shows what's going on here. It's going to take way too long to get to a signal to noise ratio of 20, even for the bright areas. And if we look for the fainter areas, let's just go for this one, 46 versus 46, it's basically the same. So we don't get an advantage of the lower read noise at Bortle 9 in terms of how long we need to expose to get a particular signal to noise ratio. And if we look at the deficit for our sub-exposure times, the 30-second versus the 10 minutes, and you're not going to use a 10-minute here, is only 3%. And down here with the read noise of 3, it's 0%. So what this is telling us is that for the extreme light pollution case, the read noise doesn't really make that much difference in terms of how long you're going to have to expose to reach a particular signal to noise ratio, and what sub-exposure time you choose. It's basically indifferent to it because all the noise is coming from the sky brightness. So let's start to put some of this together. So what's the takeaway from that? Because that was kind of complicated. It turns out that low read noise is much more important for a dark site than it is for a light polluted site. Now, as you go down in light pollution by grades, that was the worst possible light pollution. As you get less and less light pollution, it becomes more important. But it's most important for a dark site. So the impact of low read noise is most important for a dark site. And that's the main takeaway here. It has a limited effect on the total exposure time and a limited effect on the choice of sub-exposure time. It mainly is just telling us that it helps the most at a dark site. So I'm going to talk really quickly here about the sky limited sub-exposure time myth. And if you want to take a picture of that or come back and freeze it later on or whatever, there's a lot there. I could spend hours talking about this. The theory suggests that the sky limited exposure time represents an optimal balance between the read noise and the sky noise. But in practice, longer sub-exposure times are always better, with the exception of the fact that because the sky brightness is so bright, at a highly light polluted location, you're going to saturate earlier. So that's the only place where it makes a difference. The number of exposures is important to stacking for read noise, but the length of the exposure is important for sky noise. And the sky limit exposure calculation essentially decouples these two things. I know it's looking at both, but the way it's calculated decouples them. And that's a mistake. As a result, the sky limited sub-exposure time should be considered a lower limit. And I was getting these results back with my SkyTools 3 software when I first started making it do some imaging. The sky limited sub-exposure time that you can calculate is best considered a lower limit. Beyond that, you can take as long a sub-exposure time as you want. It's not really an optimum, and that's all I'm really saying here. The other thing is that it doesn't take into account the signal that you're using. And that's important. And that's another reason why I'm getting different results. I'm not just looking at the sky background or the faintest thing in the image. I'm looking at the parts that, if you're light polluted, you're more likely to be actually imaging, because in a light polluted location, you can't really image those faint things anyway. So what are the practical limits of sub-exposure time? This is what we should really be talking about: tracking errors. As you saw in that one image, those 10-minute exposures didn't make round stars. So we don't want to go 10 minutes. That's a practical limit. Satellite, if you live near an airport and there's planes flying over all the time, you don't want to throw out one 10-minute exposure when you could be throwing out one 60-second exposure. And, you know, maybe after the plane stopped coming in, you could go to longer exposures. Wind is a big consideration. Are you in a place where you have lots of accidental bumps? Animal attacks. That could happen. Trailed targets such as comets and minor planets, they're going to limit your sub-exposure time so that you don't trail them. Saturation and clipping is probably the other really big thing. You want to make sure you don't do that. So you're going to be driven to shorter sub-exposures, especially in light-polluted location. Then there's idle time, which is something else altogether. When you're calculating your optimum sub-exposure time, the sub-exposure time you want to use, basically you want to use the longest sub-exposure time you can get away with, taking into account these things. Let's talk about this idle time real quick. Idle time is the time that you're not imaging because you're dithering or you have a long readout time. So just an example here, we've got an old CCD camera with, it takes 30 seconds to read out between exposures. And we've got 60 minutes to take an image, or take our images, and then we have to be done for the night. Well, we could take 11 5-minute exposures, and the total time spent exposing is 55 minutes, or we can take 41-minute exposures, and the total time exposing is 40 minutes. This has come out several times tonight. What if I have a limited amount of time? Well, this effective idle time is really important in that case. If you're dithering, you're going to probably want to think about how much you're dithering and maybe not dither as much, because that would be a good way to increase the amount of signal to noise ratio you're going to get when you're done, because you can spend more time exposing and less time dithering. I'm not saying you shouldn't dither. I'm just saying that's something you want to consider, and a lot of people never even think about it. We don't have infinite time. All right. Is that a stop here point? Yeah, let's go ahead and stop and take some questions there. Anybody have any questions?
Yeah, I think there's a question or two here. John says, do you have any comments about how Bray Falls and company pull out detail from very long integrations? For example, the M31 oxygen arc not seen in shorter sessions.
Mm-hmm.
Are you familiar with that image?
I am. Not all of the details of the image, but I'm familiar with the idea of the image, and I've seen the image. But what is the actual question? I'm not sure I understand the question.
I've actually tried to hit that same thing, and I just wasn't getting it. And I suspect they may be right. Longer exposures are required to get above background on the oxygen.
Remember that we started with selecting targets that are appropriate for your imaging system. And a lot of that is the imaging scale. How much of the sky is being mapped to the size of your pixel? And that makes a really big difference. I do a lot of comet work, and people look at comets in their telescopes. They take images of comets, and they try to determine how bright they are, and they're just all over the map. And it's this thing where, depending on the optical situation, you're going to get a different answer. And a lot of times smaller telescopes will people using smaller telescopes will see more faintly into the coma and measure a brighter comet. And this is something that's really common. So I think if you tried to do the same thing and you had trouble, it probably had to do with your image scale and how that maps to everything else. It's all really complicated, which is why having software to figure it out is a good idea. Did that answer your question at all?
It was an online question.
Yeah, okay, that question.
By the way, that 24, that's a 4-meter telescope. You can't do 10-minute exposures without trailing stars. I don't care how well that L mount is calibrated.
Okay.
I take that from personal experience. I have one.
Okay. Oh, okay.
You have to guide.
Yeah.
So if they didn't guide, and if you have interaction with them, I would say, please guide.
They don't actually have any guiding for that telescope. what I would do is I would just not use 10-minute exposures. I would consider that a practical limit and use 300-second exposures from now on. For most of their cameras, they produce calibration images at different sub-exposure times, and it's just a lot more easier and efficient to use their calibrations. So, because it's kind of hard for me to do a sky flat or whatever with their telescope. So you've got to stick with sort of their numbers, and their numbers tend to go from 1 minute, 2 minutes, 3 minutes, 5 minutes, 10 minutes, that sort of thing. So I would just do 5-minute exposures in that case.
So you brought up another variable in here. With all of what you said,
Yeah.
guiding is an overarching factor in that setup.
That was on the last list. Yep. It's really a critical thing, and for a lot of people, their mount is maybe a little too big for their telescope, and tracking is really hard. So you're going to do 1-minute exposures, and that's all you're going to do. But the idea is the same. Stop worrying about calculating an optimum sub-exposure time. Use the longest exposure time you can get away with. It's as simple as that, and it works in every situation. That's what I'm trying to say. I know that sounds crazy. Are there any other questions?
I don't see any.
Okay. So let's talk about optimum game selection for CMOS cameras. I think we're at the end here, but we had time for questions at the end, and we've been taking questions all along, so I'm going to go a little long if people don't mind. So when CMOS cameras with adjustable gain selections first came along, it was about fitting different signals into the small ADU range these cameras had, because they're 12 and 14-bit cameras. And so things like planets and bright stars needed different gain settings for deep sky objects. So in that case, you could sort of get away with just saying, I'm going to just use one gain setting for all my deep sky work. Then 16-bit cameras started to become more the norm, and that became less of an issue. But today, we have cameras that have adjustable read modes. And those modes can sometimes be folded into the gain. You don't even know it's using a different mode when you switch it to a different gain setting. Other times, it's something you can select. So what you can get is a lot more complexity. And this is what it looks like in my software. You set up the gains for a QHY 268M. And I sort of went through the graph, and I picked out sort of the best gains for all the different situations. And you'll see that the read noise goes from 1.7 for this gain setting up to 5.7 for that gain setting. But the thing is that these things, the lower gains, the lower read noises, also track the smaller full wells for the most part. So this 1.6 here is just for 28K. If you have more than 28,000 photons, you're going to saturate. Where if you were to put up with 5.7 as your read noise, you could go all the way up to 108,000 photons. Well, now that's getting pretty complicated. So the reason I allow people to put in this whole table, all these values are now in the software. This is one of the rabbit holes I went down, is that now the software can consider that. And so how do you select the optimum gain for a CMOS camera? Well, there are two things you can do to stop saturating. And that is, the first is to lower the sub-exposure time. And the second is to change the gain. Now, saturating stars, we put up with those all the time. They can be tolerated. They're not ideal, but a lot of the times you can't get a good image of your deep sky object without saturating some stars. But the deep sky object itself is an issue. For the brighter parts of an extended deep sky object, you're going to lose important detail if it saturates. So like this HST image of M81, there's all this fine detail in the very brightest part of the galaxy. And in fact, there's this bright center core there. If this saturated, then it would all be white. And we really don't want that. So what you do is you try to make, you start picking lower sub-exposure times, and you start changing the gain settings, and then you calculate the signal to noise ratio you get for whatever you're trying to target, maybe this part here. Because you're not always just exposing for the brightest part of the camera, of the image, but you keep track of whether or not this bright part here is saturating or clipping. And if it is, you throw it out. And in the end, you just take the combination of sub-exposure time and gain setting that gave you the highest signal to noise ratio without saturating. So that's what the software does now. And that took a lot of work, actually digging into the code and changing it all. So at this point, does anybody have any questions about the optimum sub-exposure? I'm sorry, of the optimizing gain for CMOS camera?
No new questions online. Anybody in the room have a question? I guess not.
Okay. I know that's a lot of information to go over, but it's been a long 10 months. So this is sort of our summary point here. And how do we image smarter? And the first thing we can do is to find targets that are well suited for our imaging system. And there are targets out there for your imaging system that are going to make a good image that somebody else's imaging system isn't going to be well suited for. So the idea is to find those imaging systems that fit with your image scale and your camera quality, and I'm sorry, not imaging system, but find those targets that fit with your image scale, the qualities of your camera, etc. You know, when I'm out in the middle of the winter and I look up and I see Orion, this thought always goes through the back of my mind. How many people are imaging M42 right now, right? So we can use this algorithm to just go through all the objects, calculate signal to noise ratios, and figure out which of them will work well for our imaging system. So that's the first thing we can do with this. And I've got tools to do that built into my software. The second thing all of us can do is it's better to image one filter at a time rather than to do them in a round robin manner, rather than going luminance, green, red, blue, luminance, green, red, blue, or something like that. As we saw earlier, there are parts of the night where the luminance is going to be able to get a good quality image, but the blue filter's not. So don't force them to be together. You're going, if you can figure out what those best parts of the nights are, now you really want to do one filter at a time, and just for each of those filters, image them when they're at their best. You'll get better results. The next thing, rather than throw out the low quality images, avoid them in the first place. And this is big. This is a mistake almost everybody makes. Use that time for something else. This is why I say have more than one project. Because if you're just going to image that thing right down to the horizon, you're going to, hopefully, you're going to end up throwing about a bunch of images out because the scene blew up, right? The signal to noise ratio isn't going to matter that much, but your scene is probably going to blow up. And when you try to put them all together, you're going to have, you're going to compromise the detail. So rather than doing that, stop and image something else. That's point 3. Try to maximize the total signal noise that you can get in a period of time. That's point 4. So on, even if you're imaging on multiple nights, you've only got a certain amount of time available on that night. Do everything you can to maximize the signal to noise ratio you get, rather than be sort of sloppy about it. And again, that's easier said than done, but hey, I have a magic tool that will help you do that. Number 5, just always use the longest practical sub-exposure time. And practical is as we described: poor tracking, satellites, saturation, and clipping. Those are the main reasons. So now I want to take a minute to show you this new tool that I've created that takes all of that stuff that we just covered, all that smart stuff, and puts it together. I call it the Smart Project Builder. And what you do is you put in an imaging system of your location, which determines the light pollution, focal state, things like that. And then you decide what kind of imaging you want to do. And then you have two main choices. You can give it a total amount of exposure time that you're going to have available. In this case, 3 hours. That could be one night. It could be over 10 nights. Doesn't really matter. Because all of this is done for best case scenario. It's not a practical calculation. It's the best you're going to get calculation. But that's okay because it's useful to compare. And it also gives you a good target to start with. It tells you what's possible. So you could start with, I'm going to spend 3 hours on this thing total exposing. That's not imaging time, but exposing time. What can I get? And it then calculates the results and then tabulates them. And I'm going to show you that in a minute. The other approach is you can say, I'm going to give it a signal noise ratio of 20. How long is it going to take? So here's how long, what do I get in terms of signal noise ratio? Or this is the signal noise ratio I want. How long do I need to go? And then the way this works in the software is you scroll this up and down, you find the one that you want, you click it, then you click Build Project, and then that goes into the scheduler, and then off to NITA, and you image it. So what I'm going to do now is I'm going to bring the actual tool up and show an example of this. I've got to be, why didn't that work? Wow, I can't click on it. Yeah, maybe if I do this. Oh, here's the actual tool. Okay. Moving this ahead by one, so it goes, there we go. Wow, why is it doing that? Here we go. All right, sorry, it's the first glitch of the night. This is the tool, and we pick an imaging system, we pick a location, set everything to auto. We're just going to choose grayscale images, so it's just going to look at individual filters. First thing it's doing is it's got bin 2 and bin 1. Well, I don't like that. I just want everything in bin 1. So I'm just going to turn off the bin 2s. And we've got it going for 3 hours. Well, it says in the luminance filter, the exposure time is 3 hours. It's going to do 18 10-minute exposures based on my location. And by the way, I've told it for this imaging system what the maximum practical exposure time is. And it thinks it's 10 minutes. So it's going to use that. But it'll use whatever I tell it because that's a property of the imaging system and the location. So for the nuclear bulge, we're going to get a signal noise ratio of 588, which is pretty good. 63 for the main arms of M81, 12 for the halo, faint halo, and 2 in the rest. So let's say I just wanted to do that in 3 hours in one filter. That's what I would get. A total signal noise ratio of 63 for the main extent. That's what I've chosen. Let's say if I go for the very faint halo, it says I'm going to get a signal noise ratio of 2. So it all depends on what I'm aiming at. Where this gets more interesting is if we look at a color composite image. So now it's going to give us all the different options, right? And right here, we've got our good LRGB. It's come up with an apportioned exposure scheme where it doesn't use the same number of images for each filter. It's going to do 90 minutes in the luminance, 34 in the red, 28 in the green, 28 in the blue, and for a total of 3 hours or 180 minutes. That'll give us a signal to noise ratio of the final LRGB composite image of 45, right? As opposed to 34 if we do equal exposures, if we expose the same amount in each filter. I just want to point out this one here. That's a little weird. What is an LRB image? There's no G. And I know I'm almost done here, but way back when I first started doing things on the internet, I started a web page to show things that I was excuse me, things that I was observing visually, and I needed pictures. So what I do is I'd take the red digital sky survey image and the blue digital sky survey image, and I would put them together to make a color image, and I would just fake the blue as a synthesis of 50% of the red and 50% of the blue. I would fake the green. I'm sorry, I'm speaking fast and things don't always come out right. I would fake the green channel from the red and the blue because there was no green image, right? And I got nice color images. And when I started using eye telescope, sometimes I wanted to be cheap, and I thought, you know, that worked. Why don't I do that with an eye telescope? So I would just take the red and the blue filter. That way I didn't have to expose in the green. I didn't have to pay for that. And I would get this nice image just by building a synthetic green, which was just a 50% composite of the red and the blue. So what this is you just add the luminance to that. And here's the funny thing. It actually has the highest signal to noise ratio of any of these images, even better than the LRGB for 3 hours of exposing. Well, why would that be? Well, first, you're not imaging in the green, right, at all. So now you can spend more time imaging in the red and the blue, 33 minutes, 27 minutes, and 20 minutes in the luminance. Down here for the LRGB, you'd spend 28 minutes in the green. So we're doing that, but also back to that math we did at the beginning. If you were paying attention, if you make a green synthesis image, green channel synthesis image of the red and the blue, the way that combines, you're going to get a bigger SNR than you did in the stacks of the red, either the red or the blue. You're actually going to get a green channel image with a higher signal to noise ratio. So that actually improves the signal to noise ratio. That's why the LRB is actually signal to noise ratio 52 versus 45. That was just another one of those little interesting things I discovered along the way. And the idea here is you pick what you want to do. And once you've picked it, you click build project and you're basically done. And so am I. All right, so I'm done now. Sorry, I was talking pretty fast there at the end. Thank you guys again for inviting me. That's the whole talk. If there's more questions, I'll take them now.
There are some more questions. Let me read them. Let's see. Can we still take multiple exposure images sets and use HDR composition in PI to get similar final results?
Yes. That's the short answer to that.
That's an easy answer. Okay. Next question from Linda. On old school CCDs that require RBI flooding, does noise from that flooding, which can use a much higher than the dark current noise, hurt the SNR even though it calibrates out?
No, not if it calibrates out. But if it doesn't calibrate out, then I'm going to put that in the category of cosmetic defects. And that cosmetic defect isn't necessarily going to go away with stacking. So that's a difficult issue, but it is going to affect the signal to noise ratio in various spots. But it all depends on how much noise is in that signal. That's something that is difficult to study. It's just best not to have any in your image or minimize it as much as possible.
Chris, I think you answered this earlier. Do you have general guidelines about what times of night are best for each filter?
Yes.
Like rules of thumb?
No, rules of thumb, it's so complicated. There's so many different factors that go on, and you could figure out the rules of thumb for your imaging system just by looking at your images after a long time, or you could use my software to calculate what they are. But somebody else's imaging system is going to have different rules of thumb, and it comes back to this scale factor thing, and just the quantum efficiency of your detector and the filters you're using and all that. It all matters.
And
so
Greg,
rules of thumb are hard.
Greg, wasn't one of your main points that it would also matter what your object is and
Oh,
whether
yeah.
the moon's up and all that other stuff?
Yeah, and I was talking about the LRB image earlier, right? And leaving out the green. Now, if you have an object with a strong O3, that O3 line is usually situated right on the edge of the green and right on the edge of the blue. And so you probably don't want to do the LRB image for that. So there's always exceptions. Not sure where I got that from your question, but I thought they were related when I started. God.
By the way, Greg, you can stop sharing unless you're going back to illustrate something, and then you just talking to us. Yeah.
Yeah, I don't think I'm going to go back.
Okay. And you can always reshare if you want.
Okay. Yeah.
Were there other questions, Eric?
No, I think that's it.
Okay.
I hope I didn't
The concern about saturating the stars kept coming up at several places, particularly Greg, I think, was asking about it. And you're right. If you overexpose your stars, you're going to lose the star color. But there are plenty of ways to handle that besides cutting short the exposure on your nebulosity.
It's still there. Just not in the center of the star.
Mm-hmm.
So yeah.
Actually, I have a question about calculation of SNR. So we have all these stars in our image, which are bright and nicely well-defined point sources. And then everything else, like the actual nebula or the galaxy, can be a lot of that image or can be less of that image, depending on what the target is. But for either the whole image or for a given region, won't the stars drive the SNR more than the actual target, which is where you care about the SNR?
It all depends about what you care about, and you decide what you care about, and then you calculate that SNR. So I think how about this? I've been thinking, I haven't tried this yet, but I've been thinking that for some of these really tough narrowband objects, maybe you're doing a Hubble palette with an L, or maybe you're doing you're using for your luminance channel, you're using H alpha, and you're kind of going there, and you're using S2 and O3, and then maybe a synthetic green channel. There's all sorts of things you could do there, and it gets complicated, and it's going to mess up your stars. You see what I'm saying? So why not just remove them all, and then come back on another night or the same night and get some nice RGB images of the stars, and then stick those in there.
Yeah, I guess in terms of when you measure the SNR of the image, if you care about the nebula, but you have a lot of stars in the image, the number you're going to get is going to be driven by the stars and not the nebula, unless you remove the stars, right? No? No,
I mean, if you care about the stars, then you measure the signal noise ratio of the star. There's no signal noise ratio number. There's the signal noise ratio of that star, the signal noise ratio of that star.
Well, I mean, like when you measure it,
then the bright part of the image and the faint part of the image.
Like when you use the for instance, any one of the number of processes and PixInsight that measure the SNR, it gives you like one number either for the whole image or for a subregion, right?
Right.
So how do you get the SNR for the nebula and not the stars?
I can't speak to everybody's algorithm, but if you're getting the signal noise ratio for the whole nebula, then, I mean, for the whole image, then you're probably looking at the darkest parts of the image. You're looking at the background noise, or the background, or I don't know how they're doing that, to tell you the truth.
Yeah, that's what I'm wondering.
It's a compromise, whatever it is. I can tell you that it works a lot better if you just pay attention to the parts that matter to you.
Yeah, like maybe the stars take up few enough. I mean, they're all over the image. Maybe the actual number of pixels of the stars is small enough that it's still mainly driven by everything else.
It all depends on how that algorithm works. And
the other thing is that the stars are so bright that you don't usually worry about signal to noise ratio in bright objects.
No, I agree with you, and that's the problem. Is that like the number you get is going to be, your stars have great SNR, but your nebula doesn't.
Here's the solution to your problem, and that is, you use the signal to noise ratio that you can calculate for a little box.
Oh, just a little box, okay.
And you put that box somewhere you care about, and measure the signal to noise ratio in the box, because then it'll just add up the signal in the box, for your nebula we're mostly talking about here, and then it'll add up the noise in the box. or just
That
take
makes
the
more sense.
average noise for the image. Either way will work.
Could just illustrate this? Let's all imagine what a histogram looks in a typically stretched image. And you know where the big hump is over on the left. Goes up, and then it comes back down, and it goes along for a while, and then it goes way the heck out there. And do you ever see those stars way out at the end? Probably not. There aren't enough of them to bump high. And so they
That's a fair point.
just don't have that much of it, of the data is in stars.
That's a fair point.
Yeah. But stars are important. I mean, I spent all this time talking about ignoring stars, and you're right to point that out.
Yeah, I
It's
think you're
kind of
right.
hard to do both
Yeah.
well, is the problem. That's why I was suggesting doing them separately.
Yeah, that makes sense.
Well, I mean, that's okay if you're doing an RGB image, but with a narrowband image, especially a Hubble palette, which is probably 99% of all narrowband images, you put in colored stars, and the color palette of an RGB star with a Hubble palette, it just screams at you.
Yeah.
So, and star color has no meaning in a narrowband image anyway.
No, I'm, does it really have meaning anyway? I mean, we give it meaning, and we kind of have standards for the meaning, but it's not what you go out and you see with your eye for the most part. I mean, sometimes it's close, depending on how it's processed.
Our eyes are terrible sensors.
So what does that mean? What is the proper color of a star?
It means we enjoy the image, is what it means.
Yeah, that is true. And
we don't have green stars.
Yeah, green stars are bad. Green is a red flag because there's no green in the sky except that one object. There are stars that are bright near the green, but they're not narrow enough to be called green. They're really, the brightness is spread over a wide spectrum. They're not just green.
But there's
So
plenty
there's
of
nothing
green.
really green in the sky, which is why I'm so fond of removing the filter completely.
No, but there's plenty of green in a Hubble palette if you do it right.
Well, that's just your choice. That's an aesthetic choice. Yeah. I mean, in the standard Hubble palette, you're assigning a narrowband filter to green.
Right.
In the
SHO.
image, the green channel.
Yeah.
Yeah. And so you've got 3 channels, and you're using them to separate out your stuff. But if you look at where those lines are, like the O3 line, it's right between, it's sort of turquoise, basically.
It's
right
blue-green.
between red and the blue.
Right.
I'm sorry, the green and the blue.
So if you put in oxygen into an RGB image, you should really put it in as blue-green, not as blue.
Yeah, if it matters. Or you could make it yellow if you wanted to. Because we're sort of beyond the point where I used to argue with people about Mars images, right? What's the proper color of a Mars image? Well, the sky's a different color. The ground's a different color. Those things matter when you're talking about taking a picture, even on the Earth. In a gray day, look at this. Look at the ocean on a overcast day versus on a sunny day. It's a completely different color, and we don't really pay attention to that. But so Mars is a different place. You can't just have a standard photo and say, well, that's what it's supposed to look like. You can just sort of do whatever you think is the best aesthetic. That's my view, at least.
Yep, that's where the art part comes in.
Yeah. Art is so much a big part of this. And I started with this idea that, at some point, we're going to be able to get really good stretches just by pushing a button. They're already good, but I mean really good stretches. And we're not going to use the auto stretch just as a starting point. We're going to start to see AI image processing that does all of that for us. But how we do it, what colors we assign, how we handle our stars and what they look like, that's where the real art is. My job is to try to make sure that we get the best images for our purpose as possible when we're capturing them. That's what this was all about.
All right. Well, if anyone has any parting shots, or else we'll go ahead and wrap it up for tonight. Thank you so much for coming on, Greg. And this has been really instructive in kind of digging into some of the nitty gritty that I think a lot of people, we have a lot of questions in the chat during a lot of shows asking about these particulars, and now we have some particulars. So it'll be a good reference. Yeah. All right.
I don't know how many people believed me, but
yeah, I mean, if you got the equipment, you can go measure it for yourself.
Yeah.
Go find out.
Yeah. All right. Well, thanks again for inviting me, guys. And it's good.
Yeah, thanks for
good
coming
talking with you.
Yep. All right. And with that, go ahead and take it out.
Okay. Bye-bye.
Good night, everyone.